All right, in this section we're going to review some basic integration forms. The formulas on this page are all ones that we've seen before. We've learned them in Calc 1. We've used many of them previously in this course. And so we're going to just start out this chapter, which is all about techniques of integration, by reviewing some strategies we already have, like making a U substitution and then trying to recognize a form, sometimes needing to get a little creative in how we write the integral. So our first example in this section, we're really working on, or gonna maybe, I hope, have a little fun integrating these three different functions. They look really similar, right? They have all of the same denominator. The difference is in the factor of x that's in the numerator. So in the first one, we've got no x, just a constant. The second one, we've got one factor of x. And then the third integral here, it's an x squared. So let's begin. In this top one, I'm going to start out just by pulling out this factor of 4. And if you look at the sheet on the other page and kind of think about what we did earlier this semester back in Chapter 2, pretty quickly I think we'll zero in on item 15 here. This is an arctan formula, or arctan form. Where u is equal to x, so that du is dx. And a is equal to 3. So this integral is 1/3 arctan of x over 3 plus a constant. And then, we'll just clean it up by writing a single coefficient out in front. 4/3 arctan x over 3. So that's not too bad once we recognize the form, right? So integrating is all about kind of trying to recognize what it is you're looking at, what form it fits. The second one, once we throw a factor of x on the top, it is no longer an arctan form, right? The arctan form really is just the constant, or the dx just sitting there on top, not a factor of x. But this one can be done if we let u equal x squared plus 9, then du is equal to 2x dx. What we have here is a 4x, so I'm going to pull out a factor of 2. If I pull out a factor of 2, then what we're left with is 2x dx up top over x squared plus 9. And now if I make the substitution, writing it with u's, this is 2 times the integral du over u, and that's the ln form. So this is 2 ln of absolute u plus a constant, or 2 ln. Now you could have the absolute values here. I'm going to just use parentheses because u is x squared plus 9, and x squared plus 9 is positive, always positive. So the absolute value signs are optional there. All right, so we see that just the presence of a factor of x just changes the form, right, that we're looking at. In the first one, it fit an arctan form. In the second one, it fits a log form. And last, if we look at part C here, we've got an x squared. So it's no longer a log form because, we have an extra factor of x, and it's definitely not an arctan form. So looking at this, the first thing I'll do is a bit of algebra. Whenever you're working with a fraction, if the degree of the polynomial, right, a fraction of polynomials specifically, if the degree of the polynomial on top is greater than or equal to the degree on the bottom, you start by doing the division. So let's do the division. So I'm going to take x squared, I'm going to take 4x squared and divide it by x squared plus 9. So what do we multiply by x squared to get 4x squared? That's 4. Now I'll take that 4 and I'll multiply it by the divisor here, so we get 4x squared plus 36, and then we subtract this whole thing and we get a negative 36. It's a short division, right? I know I'm done because when I subtracted, I have no x's. I've got fewer x's down here after subtracting than I do in the divisor, right? So I've got no x's compared to an x squared. But the result here is that the fraction that we're starting with, 4x squared over x squared plus 9, is equal to 4, and then minus 36 over x squared plus 9. So I'm going to start just by rewriting the integral by replacing the single fraction with what we found here. And now that I have it written as a couple of different terms, I'm going to split up the integral over this subtraction. So I got the integral of 4 dx minus, and I'm going to yank out that factor of 36 from the second integral. So 36 integral 1 over x squared plus 9. Now we should be feeling better about what we're looking at here. We know the integral of 4, right? That's just 4x. And then this second integral here should look familiar. It's the one we did in part A. This is an arctan form where u is equal to x, so du is dx, and a is equal to 3. So now integrating, we have 4x minus 36 times, this integral is 1 over 3 arctan x over 3 plus a constant. And now I'm just going to clean it up a little. 4x minus 12 arctan x over 3. All right. So let's try some more integrals. You know, the name of the game when we're integrating is just trying to recognize the form that we're looking at, and it can take a bit of doing to rewrite it. You know, a lot of the time integration is just trying to rewrite something, and maybe even in a way that seems awkward at first. You know, we're kind of almost unsimplifying expressions. You know, let's unsimplify in a helpful way, or what we hope is a helpful way. All right, in this one we're going to do we're going to integrate this function, and we're going to take a step that we saw ourselves take in a previous problem, actually in just the very last one. The first thing we're going to do is just break up this fraction. Now you could break up a fraction over addition or subtraction that happens up top. So I can write this as the integral of 1 over e to the 2x plus cosine of e to the negative 2x over e to the 2x. And now we can also split up an integral over addition or subtraction. So with an eye toward like how I'm going to approach these individual integrals that we end up with, I'm going to rewrite them a little bit. So this 1 over e to the 2x, I'm going to write that as the integral of e to the negative 2x dx. And I'm going to do something similar here. I'm going to bring that e to the negative 2x in the bottom up to the numerator as a factor of e to the negative 2x. Okay, now let's approach these separately. We can, in the first integral, we could, you know, that's an e to the stuff integral, and if it fits at the integral of e to the u du, then what we have to do is choose u equal to negative 2x. If u is negative 2x, then that means that du is negative 2 dx. So we almost have our du. We're off by a factor of negative 2, and we could throw that in there. and compensate outside with a negative 1/2. Over on the other side here, this integral, a slightly different u substitution will work. And I'm gonna, you know what, to be really careful here, I'm gonna subscript my u's. So I'm gonna say I've got a u1 over on for the first integral, and I'll call this other one u2. You could also be acceptable to use a different letter. Maybe you want to use v, but I'm trying to avoid a situation where I'm using the same letter to represent two different substitutions in the same problem. That's kind of bad form. So here, if we let u2 equal e to the negative 2x, so not just negative 2x, but e to the negative 2x, then du2 is what? E to the negative 2x times negative 2. I'm just taking the derivative of e to the negative 2x dx. And I've got my du except for this factor of negative 2 that I need. So I'm going to kind of put in this factor of negative 2 here, correct for it on the outside with a negative 1/2. Now let's see what it looks like when we rewrite these with our u's. We've got negative 1/2 integral of e to the u1 du1, and then minus 1/2 integral cosine of u2 du2. We're in a position now where we know how to integrate both of these. Both of these go back to basic integral forms that are on the first page of this section of notes. They're ones that we learned back in Calc 1 that we've been, seeing a bit here and there and previously in this course. The integral of e to the stuff is e to the stuff. So I've got negative 1/2 e to the u1 minus 1/2. The integral of cosine is sine, so 1/2 sine of u2 plus a constant. And now all that's left to do is to put our x's back in. So we have negative 1/2 e to the negative 2x minus 1/2 sine of e to the negative 2x plus a constant. All right. So this next one, I guess maybe we're ruining the surprise a little bit with the introduction here. It says a disguised form of the log rule. And you know what? It totally is disguised because right now it does not look like a log rule. With the log rule, right, that basic logarithmic form is du over u. And if something fits the ln form, then u has to be the stuff in the bottom. So, okay, if u is 1 plus e to the x right now, du, I'd have to have a e to the x up there. And we don't have that, right? So clearly, like, as it's written right now, does not fit a log form. But we're going to do pull one of the oldest tricks in mathematics. I'm going to rewrite this. And I'm going to rewrite it by adding and subtracting the same thing. That's totally allowed. I'm going to add e to the x and subtract e to the x in the numerator. And then I'm going to split up this fraction. I'm going to split up the fraction and then also split up the integral at the same time. I hope that's all right. I'm going to split up just here, only at that subtraction right there, because then we have the integral of 1 plus e to the x over 1 plus e to the x dx minus the integral e to the x over 1 plus e to the x. Hopefully this is looking a little better now. We could see the log form in the second integral, I think. We're going to let u equal 1 plus e to the x. And the derivative of 1 plus e to the x is e to the x. So du is e to the x dx, and we've got that perfectly here. For the first integral, that's just equal to 1. We have something divided by itself. So we've got the integral of 1 dx minus the integral of du over u. We know how to integrate both of these, so let's go ahead and do it. The integral of 1 is just x, minus the integral of du over u is ln of absolute u, plus a constant. And now we're going to put the x's back in. So ln of, and again, with this one, we saw this happen in a previous problem. 1 plus e to the x is always positive, so we don't actually need to use absolute value signs here. So there's our result. All right, let's try another one. Here we have a disguised form of the power rule. A lot of forms in disguise in this section. You know, and I guess maybe that's just sort of a general truth with integration. Forms don't always jump out at us. Sometimes we kind of have to finesse the function to kind of get it to reveal its form to us. So in this case, you know, we have cotan x times ln of sine x. Sometimes what we do is some algebra to rewrite and see what happens, you know, see how it looks like we did in the last one. In this case, it's really all about finding the right substitution, and there might be a bunch of things to try, but I always take some comfort knowing that there's a finite number of things to try for you, really. So in this integral, what will work is to let u equal ln of sine x. And then if we take the derivative, we get 1 over sine x times cosine x dx. That's from the chain rule. So du is, now cosine x over sine x is equal to cotan x dx. And there we have our factor of cotan x. So in fact, when we rewrite this, right, this part here, there's u, and then these parts together, that's du. So it's u du, and that's a power rule, right? That's u to the first, so when we integrate, we get 1/2 u squared plus a constant. And putting our x's back in, we get 1/2 times ln of sine x all squared. I'm using brackets here so it doesn't look like I'm squaring the sign. I'm squaring the whole function, not the argument inside the function. You could also write this, and you might see it written as 1/2 times ln squared of sine x. Either's fine. Alright, sometimes we'll need to use algebra to rewrite, sometimes we just need to be clever with the substitution, or both things. Sometimes we need to use some trig identities to help us rewrite it. In this case, we're going to use one of the Pythagorean identities to help us. Now, the idea of using a Pythagorean identity kind of comes up because I see a tan squared. If I see the square of a trig function, you know, I always think, well, Pythagoras could be helpful. It's not always, but it's one of the ideas I might have. So, so the basic Pythagorean identity, it goes like this: sine squared theta plus cosine squared theta equals 1. To get the version that involves tangent, we're going to divide through by cosine squared. So this first fraction, sine squared over cosine squared, that's tan squared plus 1. And on the other side, 1 over cosine is secant, so this is secant squared theta. And this means, using this identity, this means that tan squared theta is equal to secant squared theta minus 1. So I'm going to use that to rewrite this integral. Tan squared of 2x is secant squared 2x minus 1. now we have a couple of terms. I'm going to go ahead and split up the integral over that subtraction. We know how to integrate one, and for the first one, the first integral here, it's a secant squared. And if you go back to that first page, that is one of our forms. Again, also if you just think, oh, what function has a derivative equal to secant squared, that's the tangent function. So if it's going to fit the secant squared form, then what we need to do is let u equal 2x. And then du is 2 dx. So we need to add a factor of 2, compensate with the 1/2 outside. So now this is 1/2 integral secant squared u du minus the integral of 1 dx. And now I think we're ready to integrate. So we integrate the first function, that's with respect to u, so we get 1/2 tan u minus, and then we're going to integrate 1 with respect to x, so we get x plus a constant, of course. And now the only thing left is to replace u with the x's, with 2x. So 1/2 tan of 2x minus x plus a constant. On the next page, we just have kind of a listing of different techniques we might try. Like sometimes some algebra you could do, just expand something out, you know, like multiply it out and see what happens. Sometimes separating out a fraction by addition happening in the numerator can help. Completing the square, we've already seen completing the square, how that can be helpful in section 2.3 and help us recognize one of those inverse trig forms. Dividing improper fractions, we saw that earlier in this section. We also saw an example where adding and subtracting the same thing in the numerator can help us, right? It's not the be-all end-all, but it is a step that gives us more things we can do. Right, so if we're adding or subtracting the same thing in the numerator, then we could maybe split up the fraction in a helpful way. Using a trig identity, we saw that in the last example. And then sometimes multiplying and dividing by the same thing can help. And if it's a trig function, we might try what we call the Pythagorean conjugate. A conjugate in general is what happens when you have an expression with two terms and you change plus to minus or minus to plus. So you could see here our denominator is 1 plus sine x, and we multiplied top and bottom by 1 minus sine x here. And when you do the algebra, it gives you a path to keep rewriting it. So here was just some algebra, multiplying it out to get the next fraction. From here to here, that's Pythagoras. And then you could see they split up the fraction over the subtraction that happens up top. So it's really, a lot of what we do is trying to get creative in how we write a function. If something doesn't immediately fit a form that we recognize, we could try some u substitutions, but outside of that, just keep in mind that you have algebra to use, you've got some trigonometric identities you can use. And if you get stuck, reach out and ask, and I'm eager to be of help.